one and all. Good evening. The subject name is compiler design. Now we are going to give a brief overview about the DAG representation of basic blocks. That is the one of the important phase of the phase of the compilation process. That is code generation phase, where the machine code is delivered and then it generates a block of representation of the information. This is called as a DAG representation, that is direct acid graph representation. So in this lecture, we are going to give a brief demonstration about DAG representation of blocks. So it is the main useful, these graphs, direct acid graphs, is the main important one, that is the useful data structures for implementing the transformations on basic blocks. So generally this machine, the source code has to be represented as 3 address form code generation in the intermediate code generation phase, and then it come across into several block representation, so that will give a overview of this implementation of the process. Here how it gives a picture of how the value computed by each statement in the basic blocks, and then subsequent statements of the block. So that means we are going to view a detailed version each address statement, what is happening for the for statement wise notation, block wise manner also. And we are going, while constructing this block information, a 3 address statements are to be a main important one, which is used for the purpose of denoting common sub expression within the block also. So previously we used how to eliminate the common expressions, algebraic simplifications, and these are to be used for representing the 3 address node notation. And these names are used inside the block, but evaluated outside the block and determine which statements of the block would have their computed value and outside the block. So inside the block and outside the block, what are the computations to be performed, and what is the procedure that is to be implemented as a 3 address code notation. So this is the main basic of this DAG representation, and this is called as a directed acyclic graph. Some of the things that is to be used in directed acyclic graph is, we are going to first use labels and the nodes. So nodes are to be represented, and with this nodes we have given some labeling mechanism for that particular each node. So several nodes are to be considered. Each node is separately labeled. We'll see with an example. So here leaves are labeled, that is to be as a unique identifiers. And generally we are going to use a variable name or constants. These are to be leaves are represented as variable names or constants. And every interior nodes inside this graph must be an operator symbol. So the operator symbol is to be used like plus, minus. So those are to be used interior nodes only. We cannot use for the leaves. That is not allowed. So this is the criteria 1, criteria 2 and criteria 3. Nodes are also optionally given as the sequence of identifiers for the labels. This is an optional step for the identifiers of the labels. Nodes are to be given. So there is an algorithm which is developed for construction of this DAG representation. Here we are going to give a basic block, that is an input format, and what is the output that is generated is the basic block contains the following information. That means we are going to label as each node, and for these nodes labels leaves are there. So for this label is to be called as identifier. Interior nodes are to be represented with an operator symbol. This is the procedure. Each node is attached with some node or some identifiers, and the identifier holds some set of values. That means computations may take place each and every time. So these are the main important steps which are used in the construction for the DAG representation. So first, step 1 to step 3, each statement of the block. Suppose this 3 address statement x equal to y opz, and second statement x equal to opy. Third statement, this is a 3 address statement. The second 3 address statement x equal to y op, and another 3 address statement x equal to y. So these 3 address statements can be used for the construction of this procedure. While this indicating the first step, or if y is undefined, suppose if y in the first case x equal to y op z, if y is undefined, then we are going to create a node of y. Suppose if z is not defined, then create a node z for case 1. And in this case, second step, node of OP, which is the left hand child of the node of y and right child of node z. So here in this case, we are going to check the common sub expression. And in case 2, here step 2, we are having three cases, case 1, case 2 and case 3. Suppose in case 1, case 2, what is the value of node OP? That is to be represented with one child nodes of the, so here left child of node y, where it is one child of the node y. And case 3, node n will be node y. These are the three cases which are in step 2. And first step is if y is defined, undefined, and if z is undefined. What are the two cases? And in step 3, delete x from the list of identifiers for node x and then append to the list of attached identifiers for the node which is found in step 2. And then we are going to set the node x to n. Let us see an example with the help of this procedure. First, we are going to consider a 3 address code for the block of statement. So here first point is T1 equal to 4 star I, T2 equal to A of T1, T3 equal to 4 star I, T4 equal to B of T3, T5 equal to T2 star T4, T6 equal to prod plus T5, prod equal to T6, T7 equal to I plus 1, I equal to 7, and if I less than or equal to 20, go to 3. So first step, the 4 star I. So that's why here star, as the algorithm says, that it is an internal of the operator. So previously we have taken that is internal nodes the operator symbol. So the internal nodes as the operator symbol. So that's why here this operator symbol is the star. And for the star here, left child of this one is node is to be considered with the label 4, and the right child of the node with the considered as another node with label I. So and the result which is computation of this, it performs this as stored as T1. So that is to be assigned. So T1 equal to 4 star I. That is the statement 1 representation. Whereas second statement representation, second statement represented as T2 equal to A of T1. Here T2 equal to A of T1. But we have already computed T1. So no need to compute T1 once again. But here the T1 computation is of type array type. So see, that's why here instead of I, the computation we are going to make that one is, make this as array. That is one that is known as, which is T2. Array computation T2, which is equal to A of T1. So A of T1, so A is left child of this, that is 1. And right of this one is, you have to perform previous computation, what is T1. So that is to be calculated as 4 star I. 4 star I, this total right of this one, it represents, that is T1. So A of T1, which is equal to, so now T equal to A of T1. So this index is to be calculated with the node procedure notation as one label with the index, and then the index to the left the array, and right the computation, previous computation T1. So that leads to the result of T2 equal to A of T1. And the third step is very easy, because already we have computed T3. Now the T4 equal to B of T3. T4 equal to B of T3, which is same computation as this one. Then T5 equal to T2 star T4. Now T2 star T4, which results to the T2 equal to A of T1. So T2 equal to, so B of T2 star T4 means star performed, that is left side T2 and right side T4, which leads to T5. Then prod plus T5. So like that we are going to give a that is index format. So previous one is A of T1, B of T3. So that two arrays to be represented as T2 and T4. So that is T2 is A of T1, T4 is B of T3. So the two computations here we have written as T2 and T4. A of T1, B T4 is B of T3, and the result, that is T1 that is T1 T2 star T4, which is given as result as T2 star T4. And then T5. What is T5 computation? T5, that is to be written as T5, T2 star T4. This is the computation of T5 equal to T2 star T4. And previous computation is T4 equal to B of T3. That is to be shown in this diagram. T4 equal to B of T3 and T2 equal to A of this one. T2 equal to A of T1. So that is to be, these two combinations are to be, this is the T2 computation, and this node refers to the T4 computation. And from these two, T2 and T4, we are going to get a load number label, that is the same representation, T2 and T4. We are going to extend further one level up with a star labeling node. So we have constructed a star labeling. Previously these two nodes are already available. This T2, T4, this entire thing is already available previously, previous step, same as the previous step. Now we are going to make two nodes, two transitions with the labeling node star, and we make assignment T5 equal to T2 plus T2 star T4. So previous up to this we are going to get the result which is stored in T5. Now the next step, T6 equal to prod plus T5. So what happens? We can further level up. So T5, here we got T5 equal to T2 star T4. Now the next step is T6 equal to product plus T5. So T6 equal to product plus T5. So here the plus operation is a internal operation. So plus the operator. So that's why it is an internal node to be considered. So we have considered as a node plus, and then to the left of this one product, and the right of this one as T5. So T5 is already computed. So that one we make it as a star notation T5. So that result is to be stored in T6. That result is to be stored in T6. So now we got the further part is equal to T6. Now that is to be assigned, that is T7 equal to I plus 1. So this one is up to one block of statement. This is another block you can represent. So like this, we can consider the DAG representation of basic blocks with the information. So for example, if you consider a 3-address statement, T not equal to A plus B, one 3-address statement, T1 equal to T naught plus C, this is another address statement, or D equal to T naught plus T1. So that is to be considered processed individually, as if we consider A is one operand and B internal operator is plus, and the result is stored in T naught. And T naught is already computed. So T naught, this entire thing T naught is to be computed already with this structure. So we are going to add a plus with the internal operation plus, and then to the right C. And then what we got? T1. Now again this T1 is used in this next 3 address statements. So T naught is used. Now we got one more, this one, that is refers to this one, and second refers to this one, and third refers to this one. So what is the T naught? T1 we got T1 equal to what? That is T naught. This entire thing is a T naught. So T naught plus C. So what is T naught? This is equal to, what is T naught? A plus B plus C. A plus T naught is A plus B. T naught is A plus B plus C. So that's why you got A plus B from this one and plus C. Whereas D equal to T naught plus T1. So previously we computed what? T1. Just we have to add plus T naught. So T naught also we computed. So both things are to be added with the plus operation. So that's why A plus B we have computed with T naught, the structure, And once again, T1 is also computed with one more structure. The two computations plus T1 plus T0. So T1 plus T0, which gives the result D. So D equal to this. So this is the result D. So D equal to T1 plus. So each and every time one level up with the set of labels as nodes, nodes with the circles as labels, and then perform the operation each time. And if you consider whether it is the leaves or not, other than it is an operator, and makes the three address statement which of each of the corresponding statement, and block-wise representation for each three state. So in this block it contains three statements are there. So previous example, block contains some 10 instruction, 10 address statements. Like that, each and every time we are going to represent different types of information. So in this example, we have represented a three address notation with this block product equal to I equal T plus. So like that, for each statement we are going to be represented with it. So here, the main idea about this DAG representation is each time a label to corresponding nodes, and leaves for each leaves a label is to be added, a label is to be considered with identifier, and interior nodes as that one, and that is a separate symbol to be designated, that is called as operator, the interior nodes, and each node with the list of attached identifiers, each corresponding the computed values. So in this DAG representation, we are going to verify sometimes whether the operators, sometimes the instruction. So for each of the instruction we have considered here of the time x equal to y opz. So in some cases I equal to T7 like this. Some of the cases where operator options may also available. So such type of the address statements. So if that y value is skipped, if z is not available, so our operator y and x equal to y, a simple assignment statement. So in this case, if y is undefined, then consider node of y only. If z is not undefined in that case, so if y and z is undefined in the particular case, step 1, that means only x is available, y and z is not defined. So in that case, we are going to label only the node y and node z. If y is undefined, we are going to create node y. If z is undefined, we are going to create node z. Like that, suppose if both the cases, any node is not available, or one of them is reached and another one is not reached, then we can perform the various cases, that is child node is to be considered to the right of that one, and another child node is converted to the left of this one, whether the node exists or not. So and the third one is node n will be the node of y, and if the list of identifiers which is deleted from node x, then we have to consider the append list of attached identifiers from the list. Like that, the statement notations may vary from one to another based on the three address code statements which are to be represented in this information. So this is the main useful representation from the generation of the code from that previous phase representation, that is code optimization to code generation phase, where the three address statements are to be notation depicted as a form of graph representation. This is called as directed acyclic graph representation, where the instructions are to be transformed with the help of the three address statement is the basic blocks. So here separate block of statement is to be considered as a three address statement. All the three address statements are to be represented, and any common sub-expression eliminations are there, have to be evaluated, and whether they are inside the block, outside the block, are to be considered. All these to be considers all to be depicted and evaluated by terms of this directed graph information. So only the simply following the algorithm, the leaves are to be represented, and labels are to be marked where the interior nodes are represented, and where the computation result is to be stored, and finally get the corresponding block of this address where these results are to be stored. So here in this statement, T1 is stored with some result, T2 is stored with some other result, T3 with the carry some result, so T4. So while implementing this procedure, so T1 which holds already in the step 1, the same value that is to be assigned with its index of A of T1. Again, T2 holds this some value, and this T2 value, which is the block of statement, is to be carried out in the step 5. Again, in T2, which results to be available in T5. T5 which carries the result T6. So final result which has the starting node, that is head node. So this one level up, we are going to carry out the results, and final result I equal to product I equal to T6. So this way information. So here this the T6 which equal to product plus T5. Product plus T5 and which is assigned to T6. So that is the final result which is to be available in this example. So product T6 equal to product T6. So product plus T5. What is the T5? T5 equal to T2 star T4. So T2 has separately calculated, T4 is separately labeled, and to perform the star operation. So T2 step. So what is T2? T2 contains A of T1, T4 contains B of T3. So A of T1 and B of T3. So here once again we are going to perform. So the operation result, final result, the entire result which is stored in T6. So T6 is the final result, and this is assigned to prod equal to T6R. And if there is any assignment levels which then we are going to perform one more level up with the corresponding node representation and label it. If further level approaches are there, you can determine the result. So this is the final representation of the DAG, that is directed acyclic graph, which are frequently used for the in place of the code generation phase. So all the contents which are available, this that is compilers techniques, that is Alfred Sithivilman. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.